Okay. Let me make sure everything is where it needs to be. There's this there. Okay, good morning, guys. If you are part of section 002 that normally meets at 9:30, you may notice a few new names floating around in the Zoom meeting today. This is really my fault because my alarm didn't go off this morning. I have an 8 a.m. class that because my alarm didn't go off in time for, it didn't go off at all, honestly, so I woke up around 8:30 going, oh shit. I've invited them to come sit in on your class today because you're at the same place. So the room may be a little bit more full than normal. You may see some names that you're not familiar with, but don't panic. It's just students of mine from another class coming here because I fucked up earlier this morning. Today we're going to continue talking where we left off last time with Taylor series. I'm going to show you some more challenging examples. So let's dive in. This is our sections 002 and 001 here today. And it is 11, 16, 20. Oh, and of course, when technology fails you, it just really likes to fail you all at once. All right. So today, we're going to talk about more examples of Taylor and MacLaurin series. Now remember that a MacLaurin series is just a Taylor series that's centered at 0, and most of the important examples we'll look at are actually MacLaurin series. But it's not wrong to call them Taylor series either. A quick recap of series we know so far. We have, of course, the geometric series. You have your natural log series, ln 1 plus x. The inverse tangent series. And then last week, we cooked up the series for e to the x. This was our first example that we did using the Taylor series table. And we also cooked up the series for the sine function in one of the sections. But the other section didn't get to see that. So today, I'm going to find sine and cosine series. And then we'll also look at one other kind of big famous example. Okay, so these are the ones that we definitely need to remember so far. Let's cook up sine. So for those who saw this before, think of this as a review. For those who haven't seen this before, of course, this is going to be fresh. All right. So definitely each of these you guys need to know. And there's going to be two more that you absolutely need to know cold, and those are sine and cosine. First sort of example here. We're going to find the MacLaurin series for f of x equals sine x. So we have to make our table. when n is 0, if you differentiate sine 0 times, it just stays sine x. And if you plug in 0, you get 0. So C0 is 0 over 0 factorial, which is 0. Remember how this table worked. Over here is n. Over here is the nth derivative of your function. This is the nth derivative of your function with the center plugged in. Since this is a MacLaurin series, the center is 0. And then Cn, this is what you get by dividing this guy by n factorial. So since n was 0 here, I took this and divided by 0 factorial. And the row for n equals 1, f prime of x, the first derivative of sine is cosine. If you plug in 0, the cosine of 0 is 1. So C1 here is 1 over 1 factorial, which is just 1. When n is 2, if you differentiate twice, the derivative of cosine is negative sine. When you plug in 0, sine of 0 is 0, so negative sine of 0 is still 0, so C2 is 0 over 2 factorial, which is 0. When n is 3, the third derivative of sine, which is what you get when you differentiate negative sine of x again, is going to be negative cos x. And negative cos of 0 is negative 1, so C3 is negative 1 over 3 factorial. When n is 4, the fourth derivative here, derivative of negative cos x is positive sine x. And the sine of 0 is 0. So C4 here would be 0 over 4 factorial, which is 0. I'm going to do one more. When n is 5, the fifth derivative is just cosine. Cos of 0 is 1. So C5 here is 1 over 5 factorial. And this is one of these examples where it's not super easy to write down a nice formula for the CNs. I'll show you. So like, C0 is 0, C1 is 1, C2 is 0, C3 is negative 1 over 3 factorial, C4 is 0, C5 is positive 1 over 5 factorial. So Cn here, there is a formula. It's just not pretty. It's 0 if n is even, and it is negative 1 to the k over 2k plus 1 factorial if n equals 2k plus 1 is odd. This is sort of the nicest way to write a formula that gets both the patterns for the odd guys and the even guys all being 0 in one place. But this isn't how anybody would write down the series. The nice way to write down the series here is to say, okay, so sine of x should be sigma n from 0 to infinity Cn x to the n, right? So it's a MacLaurin series. The center is 0, so Cn x to the n instead of like x minus 2 to the n. And then just start writing it out. So that's C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus C5x to the 5, and so on. And we look and see if there are some patterns here. C0 is 0, plus C1 is 1, so that's just x, plus C2 is 0, plus C3 is minus 1 over 3 factorial x cubed, plus C4 is 0, and then C5 plus 1 over 5 factorial x to the 5. So if we stop writing the zeros, this is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5. And so the next term would be minus 1 over 7 factorial x to the 7, and then plus 1 over 9 factorial x to the 9, and so on. So you notice the pattern here is exactly what we said it was here, exactly what it looks like from this column. All of the even terms are 0. And then the odd terms, the ones that survive, they alternate from positive to positives. The next one would be negative. And what you have is you're dividing by the odd factorials. So it's alternating and dividing by the odd factorials. And all the even-powered terms are dead. So if I want to write this in sigma notation, here is the thing that you would need to save. Sine of x, or sine of anything, is sigma n from 0 to infinity. Negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And the interval of convergence here is negative infinity to infinity. So if you had a hard time following this last time, or if your class didn't get to see this last time, this is the power series, the MacLaurin series, for sine of x. You kind of take the odd part of the e to the x series and then make it alternate. There's a reason for that. Questions on this procedure here, on this result? Okay. So how do we get cosine?
Wait, I have a question.
Yeah.
Really quick. Where did the x to the power 2n plus 1 came from?
So if you look at what we have here, this is x to the 1, x cubed, x to the 5, x to the 7, x to the 9. These are only odd powers of x that are showing up, right? So this is 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1. Your sort of generic odd number is always in the form 2n plus 1.
I see, thanks.
Yep. Yeah, odd numbers are always one more than an even number, right? So 2n is your even number, and then plus 1. Okay. So what about a series for cosine? We have a series for sine. I could start over and make a table for cosine. But if we're clever, well, option 1 could make a table. Blah, blah, blah. Same as sine. Same as we did for sine. Or if you're clever, call that cosine is the derivative of sine. Let's do 2. So I want a series for cosine. Find the MacLaurin. I know that cos x is the derivative of sine x. And I know that sine x has series sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. So if I differentiate this series, I should get a series for cosine. That means I want to differentiate with respect to x. So the sigma, the negative 1 to the n over 2n plus 1, those are constants with respect to x. It's just this piece that I differentiate. So the 2n plus 1 power comes down, and I'll have x to the 2n plus 1 minus 1 is 2n. And since this series doesn't have a constant term, right? We saw that a minute ago. The first term of the series here is x, not a constant. You don't bump the starting index. This is d dx of x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus blah, blah, blah. Does not have a constant term. So you don't bump the starting index. And now the only thing to do is to kind of clean this up. You've got a 2n plus 1 here and a 2n plus 1 factorial there. So what is 2n plus 1? 1 over 2n plus 1 factorial times 2n plus 1. How do we simplify that? Well, that's the same as 2n plus 1 over 2n plus 1 times 2n times 2n minus 1 all the way down to 3 times 2 times 1. You can cancel the 2n plus 1s, and what's left is just this. But that's 2n factorial. So this whole thing is 1 over 2n factorial. These are sort of two little bits of side work. And that means that what we have here is 2n factorial x to the 2n, and we didn't need to bump our starting index because the series we were differentiating doesn't have a constant term. So this is the power series for cosine. This is the MacLaurin series for cosine. Cos x has power series expansion sigma n from 0 to infinity, negative 1 to the n over 2n factorial x to the 2n. Very similar looking to the series for sine. It's just this is the even terms, whereas sine is the odd terms. And the IOC here is again negative infinity to infinity. Because when you integrate or differentiate a series, the radius of convergence can't change. And the radius of convergence for the sine series was infinite, so the radius of convergence for the cosine series has to be infinite as well. All right. So these are our last two super important examples. You now have series for the 1 over 1 minus x, and you can get series for all sorts of rational functions from that. You have series for natural log 1 plus x, inverse tangent of x, e to the x, sine of x, and cosine of x. Most functions can be built up as combinations of those things. So you can now find power series for pretty much any of the functions that you'll have messed with in this class. I do want to work through one or two more examples using that table though, because I think working directly with that table is kind of challenging. And that's the last thing I want to give you guys a little bit of practice with today. And specifically, I want to look at something that's kind of similar to a binomial series. So I'm sure many of you have heard of the binomial theorem. It's an official part of the pre-calculus class here at Santa Fe. So if you took pre-calc here, you should have seen something about the binomial theorem. The classical binomial theorem says if n is, actually let me use a different symbol than n here. If m is an integer, a positive integer, then x plus y to the m can be written as the sum from n equals 0 to m choose n, x to the n, y to the m minus n. Where m choose n, this thing in the middle here is the binomial coefficient. It's usually expressed in terms of factorials as m factorial over n factorial times m minus n factorial. But can also be written other ways. Can be written as m times m minus 1 times n minus 2, all the way down to now stopping at a, what would this be? M minus n plus 1. And then downstairs here we would have n times n minus 1 down to 1, right? N minus 1. Yeah. But most people think of it like this. This can be extended to what's called Newton's binomial theorem. Now, I think the way your textbook gives this is like this. It's x plus 1. They don't let y be a separate variable. They just use the one variable. X plus 1 to the m is an infinite series, n from 0 to infinity. And they write the binomial coefficient still, but then they write it in a different way. They write it something like this. I'll make sure I use the same notation. It's a little misleading. Yeah, same thing. Yep. Where they say here, m choose n is m times m minus 1 times m minus 2 down to m minus n plus 1 over, they just leave the bottom as n factorial. This is correct. There's nothing wrong with this. And the nice thing is that this works for any real number m. So this will allow you to get a power series expansion for things like the square root of 1 plus x, or 1 over the square root of 1 plus x, all sorts of stuff. The catch is it comes in terms of these weird binomial coefficients, which are easy to write down if m is a positive integer, but are kind of hard to write down if m is not a positive integer. So here's what I am going to tell you guys. First, look at some of the examples in here. They'll do an example explicitly like this. And then you'll see them trying to interpret this 1/2 choose n or -1/2 choose n binomial coefficient, which is not a pretty thing. I don't advise that you memorize this. I'm not putting this in the list of series that you must know cold. The series that you must know cold are just the ones we've talked about, the geometric series, natural log, arctangent, e to the x, sine x, cos x. This more general binomial series, you don't have to know it. You're welcome to know it. You're welcome to memorize it, but I'm not requiring you to memorize it. I do require, though, that you're able to come up with the results. So let's see kind of where this comes from by doing an explicit example. So let's find a MacLaurin series for the square root of 1 plus x. How are we going to do this? By building the table. And the reason I'm running you through this is because these particular problems, the pattern in the CNs, are kind of hard to detect. And I want to give you practice with it. So this is going to be a difficult problem, just as a sort of warning. The things that we'll be writing down here are a little bit funky looking because the repeated derivatives of this are a little bit weird. Right, this is 1 plus x to the 1/2 power, right? So if I differentiate 0 times, Hamlet, stop, no bub. Then this is 1 plus x to the 1/2, no differentiation. And when you plug in 0, you get 1 plus 0 to the 1/2, which is just 1. So C0 is 1 over 0 factorial. If you differentiate once, f primed is 1/2 times 1 plus x to the -1/2. So f primed of 0 is 1/2 times 1 plus x to the -1/2. That's 1 to the -1/2, which is still just 1. So this is 1/2. So C1 is 1/2 divided by 1 factorial. If I differentiate again, f double primed is 1/2 times -1/2, this is a negative, times 1 plus x to the -3/2. So f double primed of 0 is 1/2 times -1/2 times 1 to the -3/2. But this piece is just 1, so that's 1/2 times -1/2 over 2 factorial. The third derivative, I differentiate again, is 1/2 times -1/2 times -3/2 times 1 plus x to the 5 halves. And when you plug in x equals 0, this piece will become 1 to the negative 5 halves. So f3 of 0 is just the 1/2 times negative 1/2 times negative 3 halves. So C3 is 1/2 times negative 1/2 times negative 3 halves all over 3 factorial. I'll do one more, and then we'll see if we can't start finding a pattern. If I differentiate a fourth time, the fourth derivative here, it's 1/2 times negative 1/2 times negative 3 halves times negative 5 halves times 1 plus x to the negative 7 halves. So f4 of 0 is just this product of constants, 1/2, negative 1/2, negative 3 halves, negative 5 halves. And so C4 is that product of constants all divided by 4 factorial. Okay. So let's stop with all of these calculations and see if we could guess what the next term here would be. Looking at what we have so far, can anybody guess what C5 would look like?
Would it be the same like numerator, but instead with like additionally there would be a negative 7 halves over
Good.
factorial?
Yeah, exactly. So it's this product would go one further. So it would be 1/2 times negative 1/2 times negative 3 halves times negative 5 halves. And then the next term here, what's going on? These numerators are odd numbers. So the next term would be negative 7 halves. And then downstairs is always this n factorial. So downstairs here would be a 5 factorial. Okay, so we're to a place where we can guess what the next one looks like now. Maybe we can figure out what the nth one looks like. I think in order to do that, we should try to simplify these just a little bit. So C0 is just 1. C1 was 1/2. C2 was 1/2 times negative 1/2 over 2 factorial. So what do we have there? Well, these 1/2s, I could bring those 2's downstairs. I can treat this as negative 1 over 2 to the 2 times 2 factorial. I could treat this one as negative 1 squared over 2 to the 1 times 1 factorial. Negative 1 squared. I can call this negative 1 cubed if I wanted to. Or negative 1 to the n minus 1. Yeah, we could even do that. We can call this negative 1 to the 0, negative 1 to the 1 if we wanted. This is probably going to be the easier way. C3. So I'm just trying to write these as a function of the index. C3 was 1/2 times negative 1/2 times negative 3 halves, right? All over 3 factorial. So what do we have here? I've got 2 copies of negative 1, right? One from each of these. So that's negative 1 squared. Downstairs, I've got 2 to the 3 times 3 factorial. And then upstairs, I have this product, 1 times 3. right? 1 times 1 times 3, but just 1 times 3 is fine. The next guy, C4, first I'll write it as we had it written here, was 1/2 times negative 1/2 times negative 3/2 times negative 5/2 all over 4 factorial. What sort of terms do I have showing up here? Well, I've got how many negatives? 1, 2, 3 negatives, right? So that's negative 1 to the 3. And then how many 2's do I have downstairs here? 1, 2, 3, 4. So downstairs I have 2 to the 4 and a 4 factorial. And then what's left upstairs is this product, 1 times 3 times 5. And now we'll start to see the pattern. Negative 1 to the n minus 1. Downstairs, 2 to the n times n factorial. And then upstairs, this sort of weird product, 1 times 3, 1 times 3 times 5. The next term, I'll prove that this works. But then we are going to take it for granted from there. I have 1, 2, 3, 4 negative pieces, so negative 1 to the 4. The numerators here are 1 times 3 times 5 times 7, so 1 times 3 times 5 times 7. Downstairs here, I have 2 raised to the power of 1, 2, 3, 4, 5, 2 to the 5 times 5 factorial. So the nicest way I could hope to write the CNs here is as negative 1 to the n minus 1. Downstairs, we have a 2 to the n times n factorial. And then the weird thing upstairs is this product, right? 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7. That's 1 times 3 times 5 times 7, dot, dot, dot. Going out to where? Well, it's only odd numbers, and it ends, it's the product of the first 3 odd numbers. So here n is 4, and this ends at 5. Here n is 5, and this ends at 7. That's like 2n minus 3. Let's say 2 times 3 is 6 minus 3 is 3. 2 times 4 is 8 minus 3 is 5. 2 times 5 is 10 minus 3 is 7. Yeah, this is ending at 2n minus 3. Which means the square root of 1 plus x can be expanded as a power series. Cn x to the n like this, where these are the CNs. The only catch is that this formula doesn't work if n is equal to 1. It might not work if n is equal to 2 either. Yeah, if you plug in n equals 1, this product isn't defined because 2 minus 3 is negative. It doesn't make sense here. If you plug in n equals 2, it actually works okay. Yeah, so this is okay as long as n is greater than, definitely not 0, 1. Yeah, greater than 1, greater than or equal to 2. So you have to pull out the first 2 terms. Like this. The n equals 0 term and the n equals 1 term don't follow this pattern. So I have to pull them out. But I know what C0 is, and I know what C1 are. C0 was 1. C1 was 1/2. And then for n greater than or equal to 2, I can use my formula, which is -1 to the n minus 1, 1 times 3 times 5 up to 2n minus 3, divided by 2 to the n times n factorial times x to the n. So this would be what our final answer looks like here. And this is admittedly a very hard problem. But I wanted to go through something challenging like this for you because this is on the upper end of the sort of thing I could ask you to do in, say, a homework problem. For a little bit of context, when I taught this class at UF, this was an exam problem. I wouldn't do that to you guys. That's a little bit savage in my opinion. But it's manageable. And the whole game is about making that table to look for the CNs and looking for patterns in the CNs, finding a nice way to write them. So I'll give you a second. Let me zoom out here a little bit to sort of see what's going on and write things down, and then ask questions as you'd like to. I think you'd agree that from the formula in the textbook, you would never see that this is the series. This is why I don't like teaching that formula for Newton's binomial theorem. But at the same time, I hope you can see how this really wasn't that bad of a process. You just differentiate again and again, plug in 0, and then try to look for a pattern. Is there any particular part of this that we'd like to look at more closely? Okay, any questions for me on what we did here or why? Where anything came from? I can go back to our table here. This is where we started. So the formula we were able to eventually come up with. You remember when we saw products like these way back in the section on the ratio test? The reason we showed products like these back in that section on the ratio test was so you'd be able to handle them here. So if I finish writing the result on this page, it was so Caleb's asking, how did I get the 2n minus 3? I noticed that these are all odd numbers, right? 1 times 3, 1 times 3 times 5, 1 times 3 times 7. And the question I ask myself is, how does the odd number at the end here relate to the number here? Right? So is this product like 1 times 3 times 5 out to 2n minus 1? Because 2n minus 1, that's one way to write a generic odd number. Or is it 1 times 3 times 5 out to 2n plus 1? Well, if you look, when n is 3, the last number here is 3. So So if I plug n equals 3 in here, then this would be 6 minus 1 is 5, and this would be 6 plus 1 is 7. So it couldn't be either of these, because when n is 3, I need it to end in 3. So another way to write a generic odd number is as 2n minus 3. And I ask, does that work? Okay, well, when n is 3, then this would be 1 times 3 times all the way up to 2n minus 3. Well, 2 times 3 minus 3 is 6 minus 3. That is 3. Okay, it worked here. Does it work here? Well, 2 times 4 minus 3. 2 times 4 is 8, minus 3 is 5. Okay, yeah, that did work. What about here? 2 times 5 minus 3. That's 10 minus 3. That's 7. Did this end in a 7? Yeah. So this was my guy. In other words, Caleb, I know that odd numbers are always 2n plus 1, 2n minus 1, 2n plus 3, 2n minus 3. Odd numbers are always 2n plus or minus something odd. So I'm asking myself, just where does this end in relation to the index? If the index is 3 and the product ends at 3, the index is 4, the product ends at 5, the index is 5, the product ends at 7, and I try to find a formula for a generic odd number that matches those things. And here 2n minus 3 works. Yeah, it's not entirely obvious. Okay, cool. While we're here, because I know this is challenging, I think Patrick JMT has at least 1 or 2 things like this. Oh, maybe not. Okay, no, he doesn't. I'll try to find some stuff to add to your modules where you can watch more examples like this that are challenging. But that is it as far as working with the Taylor series table. What I wanted to do today, I want to get through one of these tough examples, and of course the sine cosine examples. But that's not everything we wanted to do today. If you have series, I mean, what's the point of coming up with series? It's to get shit done with them. So let's see if we can get some shit done with series. This is a fairly tame example because here we can use the 1 over 1 minus r stuff. To say that 1 over 1 minus x to the 9 is sigma n from 0 to infinity x to the 9 to the n, which is sigma n from 0 to infinity x to the 9n. Which means that x over 1 minus x to the 9 is x times this series has this as a series expansion. Therefore, the integral x over 1 minus x to the 9 dx is the integral of this series. And this integral is a tough integral, right? I mean, you don't want to try to do this by hand. It's not going to be pleasant. You'd have to factor this denominator. It's not a super easy thing to factor. It's a 9th degree polynomial. and then do quite a lot of partial fractions and pray that everything comes out nice and you don't make any mistakes. But you can evaluate it as a series pretty easily, rewriting the integrand, this function, as a series using just the geometric series trick, and then integrating that series, following the rules that we know for integration of series. So this is capital C plus sigma n from 0 to infinity. You're going to add 1 to this power, so you'll have x to the 9n plus 2, and then divide by that new power. And that's it. Easy peasy lemon squeezy. You might like to know what is the interval and radius of convergence. If you wanted those things, then you would run the ratio test, just like we did back in 11.8. Another example of an integral that you could not have done before today this is called the sinc integral. And there is no closed form for this antiderivative. There's no way to do this using normal tricks without infinite series. But we do know that sine x has series sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. So if you divide by x, that's 1 over x times this series just has the net effect of bringing that power down by 1. X to the 2n plus 1 divided by x is just x to the 2n. So the integral of sine x over x is the integral of sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n dx. And now we do the integral just like we do any other series integral. You add 1 to the power of x and divide by that new power. Don't forget your plus c out front. The index never changes when you integrate. So you have -1 to the n. You've got your 2n plus 1 factorial, just chilling. And then you have another 2n plus 1 from the integral and x to the 2n plus 1, like this. So the power went down when we divided by x, but then when you integrate, it goes back up. And just using the regular power rule. Just add 1 to the power, divide by the new power. Same thing we used in the very first week of the semester. Questions on either of these examples? Evaluating series, integrals as series. So first you rewrite your function as a series, then you integrate it. That's all. Rewrite your function as a series, then integrate that sumbitch. Another sort of problem like this that we can solve now that previously was challenging are certain limits. So using series to help with limits is definitely a thing. Does everybody remember this limit? Lim x to 0 cos x minus 1 over x. This is a special trig limit from Calc 1. So I could say I want to solve this limit using series. Of course, there are other ways to do it. But if we wanted to do this, just as an example, we would begin with what cos x is. Cos x is sigma n from 0 to infinity, negative 1 to the n over 2n factorial x to the 2n. And here I would write this out. When n is 0, you get 1. When n is 1, you get minus x squared over 2 factorial, and then plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, and so on. Which means cos x minus 1 is all this stuff minus 1. And of course, if you subtract 1 from all this, this 1 and this 1 will cancel, and you get negative x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus the next term here would be x to the 8 over 8 factorial, and so on. All of this is being divided by x, which is the same as multiplying all of that stuff by 1 over x. And when you distribute the 1 over x, you get negative x over 2 factorial plus x cubed over 4 factorial minus x to the 5 over 6 factorial plus x to the 7 over 8 factorial, and so on. Sorry, so this is this, yeah, sorry, I divided by x without telling you guys here. So cos x minus 1 is the numerator, and then the x is downstairs here, so we divided by x. Here, the 1's go away, and then here, we write the dividing by x is multiplying by 1 over x, and then here we knock each of these powers down by 1 because we're dividing each term by x. So the limit as x goes to 0 of cos x minus 1 over x is the limit as x goes to 0 of this thing. Sorry, not x squared, just have it negative x over 6 factorial, so 7, 8 factorial, and so on. And if you send x to 0 in this expression, since every single term has an x, you get 0. You can also get the sine x over x limit that you remember from Calc 1 in this manner. But I think it would be fun to do a slightly more complicated example. So let me grab one more complicated example here, and this will be our last problem for today. So this table you should know well. The last row in this table, I don't hold you guys responsible for, but everything else you must know. This can be useful for summing series. We've seen that. Integrals, limits. Let's do this one. E to the x minus 1 minus x over x squared. Minus x over x squared. Yeah. So you see right away, if you try to plug in 0, you'll have e to the 0 minus 1, that's 0, minus 0. So the top is 0, and the bottom is 0 also. So you can't do that. You could use L'Hopital's rule here, although I think you might need 2 runs of L'Hopital's rule to make it work. But the problem asks us to do it as a series. So I'll begin with the series for e to the x, which is sigma n from 0 to infinity, x to the n over n factorial, which is 1 plus x squared over 2, right, 1 over 0 factorial plus x over 1 factorial, plus x cubed over 3 factorial, and so on. Now 0 factorial is 1, so that first term is just 1. 1 factorial is also 1, so that next term is x. 2 factorial is 2, so this is x squared over 2. 3 factorial is 6, this is x cubed over 6, and so on. Which means e to the x minus 1 minus x is this stuff, 1 plus x squared over 2 plus x cubed over 6 plus dot 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 minus 1 minus x. So this is 1 minus 1, those go away, and this is x minus x, those go away, and we get x squared over 2 plus x cubed over 6. The next term would be x to the 4 over 20, 4 factorial, which is 24, and so on. So now, if you divide everywhere by x squared, that's 1 over x squared times this. And if you distribute the 1 over x squared, you knock each of these powers down by 2, you just get 1/2 plus x over 6 plus x squared over 24 plus the next term would be x cubed over 5 factorial and so on. But the important thing is now you can send x to 0. Here, these terms all have x's, so they'll all go to 0. So will all the higher order terms. But that first term doesn't. So the limit is just 1/2. These are pretty much all the things that we like to do with Taylor series. Integrate them, differentiate them, use them for limits. There are some situations where you may want to use the estimation theorem for alternating series, right? For example, here in the example before the one that we just did, where they integrate from 0 to 1, e to the negative x squared, they're able to get this series for the antiderivative, and then plugging in bounds, they get this series. But if you want to know how accurate your approximation is from the first, say, 5 terms of the series, you need that estimation theorem that we used. But there's nothing magical going on here that you haven't seen before. Everything else really is just stuff that we've done. I'm not going to have you guys multiplying and dividing power series. A brilliant and rather hilarious man once told me, if you ever find yourself trying to divide 2 power series, you fucked up somewhere. Go back and try something else. There's a better approach. It is possible to multiply power series, but they do not multiply the way you might think they do, not term by term. They multiply like polynomials multiply. You have to kind of FOIL everything out. But if both of them have infinitely many terms, that gets very complicated. Similarly, division is not something that you guys are going to have to do. So that is about all I have for you guys today. Maybe we should do one example here where we're going to use the estimation theorem. So let's come back here. Let's evaluate the integral from 0 to 1 of e to the negative x squared dx with error less than 0.001. It doesn't tell us to do this, but we're going to need series here. And then in order to get control over the error term at the end, we're going to need our estimation theorem for alternating series. So I begin with the fact that e to the u can be written as sigma n from 0 to infinity u to the n over n factorial, and plug u equals negative x squared. So e to the negative x squared is sigma n from 0 to infinity negative x squared to the n over n factorial. And this I can clean up quite a bit. That's sigma n from 0 to infinity negative 1 to the n x to the 2n all over n factorial. Which means the integral from 0 to 1 of e to the negative x squared dx is the integral from 0 to 1 of sigma n from 0 to infinity negative 1 to the n, I'll write it like this, over n factorial times x to the 2n dx. Now this is a definite integral rather than an indefinite integral, so I won't need a plus c, but I will need to evaluate between bounds. So when I take my antiderivative here, the negative 1 to the n over n factorial just come along to the right. X to the 2n is going to become x to the 2n plus 1, and I'll get a 2n plus 1 downstairs like this. I don't know if you guys can read that. 2n plus 1 downstairs. And then this whole thing needs to be evaluated from x equals 0 to x equals 1. You can think of this as being written out long ways. When n is 0, what do we get here? This is x. And then when n is 1, we'll have minus 1 over 1 factorial, 1/3 x cubed. And then when n is 2, you'll have plus 1 over 2 times 5. That's x to the 5 over 10, and then minus will be x to the 7 over 0, 1, 2, 3 factorial times 3 factorial 6 times 6 plus 1 is 7. 6 times 7 is 42. we're evaluating this from 0 to 1. So when you plug in 0, the lower bound, you really do get 0 because every term here has an x. So what we get is just what you get when you plug in 1, which is negative 1 to the n over n factorial times 2n plus 1. And if I want to approximate this, so how many terms are needed to approximate with error less than 0.001? Well, this is an alternating series. The bn's here are 1 over n factorial times 2n plus 1. I'm not going to talk about convergence here. I know that this series converges because the power series that I integrated has an infinite radius of convergence. But I do want to talk about the estimation stuff. So I need to solve the inequality bn plus 1 is less than 0.001. In other words, 1 over n plus 1 factorial times 2n plus 1 plus 1 is less than 1 over 1,000. Right? 1/10, 100th, 1,000. Not a whole lot more I can do algebra-wise. That's 1 over n plus 1 factorial times 2n plus 3 is less than 1 over 1,000. And then from here I would take reciprocals. And from there it's more of a guess and check sort of thing. So this is n plus 1 factorial times 2n plus 3 is greater than 1,000. It'll happen pretty quick. Let's play around. Let's try n equals 2. That's 2 plus 1 factorial times 2 times 2 plus 3. Okay. N plus 1 factorial times 2 n plus 3. Call this f of n. Yeah. Ignore the graph, please. So f of 2 we just computed is not big enough. What about f of 3? F of 4. F of 4 is large enough, right? So when n is 4 here, so this, which is true, as long as n is greater than or equal to 4. So you need at least 4 terms. I.e., the integral from 0 to 1 e to the negative x squared dx is equal to, it's definitely exactly equal to the sum from 0 to infinity, negative 1 to the n over n factorial times 2n plus 1. But that itself is approximately equal to, what are my first 4 terms? When you plug in, this is going to be 1 minus 1/3 plus 1/10 minus 1 over, if I plug in n equals 3, this is 3 factorial 6 times 2 times 3 plus 1 is 7. And 6 times 7 is 42, right? Yeah. So this approximation will be accurate to 0.01 error. Cool stuff, right? So the good news is this marks the end of our discussion of series. You made it. This is the last bit of anything we're doing with series. It has to do with solving integrals, limits, and other things in terms of series. After you finish this homework, I won't be dropping any fresh content related to series on you. This is the end. But there is going to be a new homework this week, and it is going to have some of these slightly harder problems relating to infinite series on them. Let me take a quick look here and see, because I don't think I gave you guys any of these on the last one. Fuck this thing. I'll take a look. Maybe I won't hit you with any more infinite series homework this week. Maybe we'll just start talking about the applications, and I'll just leave these to the study guide. But I would hate to do that. I feel like you really do need practice with these things. So let me see if I didn't give you anything like this last week. And then we had, yeah, you had these. Okay, so here's what I'll do. I will leave the homework from last week, which had those difficult problems at the end, open for a little bit longer. I'll leave that open until Wednesday. And then on Wednesday of this week, next time we meet, we're going to shift gears. We're going to switch from talking about series. We'll be all done with the series stuff, I promise. And then we're going to start talking about things like polar coordinates, surface areas, other sort of application problems that don't involve infinite series. So you can breathe easy. You are done with series as soon as you finish this homework. Exam 3 will have power series stuff on it, but it won't just have power series stuff on it. It'll have other stuff as well. And then, of course, the final will have this material on it also. But you're done learning new infinite series stuff. You've made it through the hard part of Calc 2. So give yourself a round of applause. Take a little rest in your brain, and then come back and make sure you really do understand this stuff so it doesn't bite you in the ass on test 3. But congratulations. Yeah, that's a good question. Exam 3 is going to be towards the end of the semester. I think, when is our last day of class here? Is it like December 4th or December 11th? It's probably the 4th, right? So usually I do exam 3 on the last day of class, unless there's a reason not to. Yeah, 12/4 is your last day of class. So exam 3 will be on 12/4. You got some time. So 2 weeks from this Friday.
And then our final will be the 7th.
Yep. Let me make sure. So which one of these did I pull up? And it depends on which section you're in. If you're in section 1, it'll be on the 7th at 8 a.m. If you're in section 002, you're in section 002, it will be oh, it looks like they're both at 8. Yeah, so double check. Look in East Santa Fe and make sure that everything lines up. Oh no, yeah, different dates, right? Yeah. So the final depends on which section you're in. Look in Canvas or look at East Santa Fe or in your syllabus, but they're not the same for both classes. But test 3 will be on the last day of class, which is December 4th, and then the final will be at whatever day your syllabus or East Santa Fe says. All right, any questions for me before we sign out, guys? Okay, you've all done well to get here. Hang in, push a little bit harder, and you'll be through the hardest part of this class. Then you can relax a little bit. The last bits of material that we're going to be covering here, like polar coordinates and some of these application problems like arc length and surface area, they're not bad. They're really not bad. They're considerably easier for most people than the infinite series stuff. So make sure you put the love into this last little bit of power series work. Make sure you really understand it and aren't making mistakes in the problems. And you should be good to breathe a little bit easier for the remainder of the term. That is it from me. I will see you guys next time.